Islam Indonesia, padamu kami berjanji, majukan studi, giatkan bakti untuk pembangunan pertiwi, syariat Islam amalan kita, tegakkan iman dan tauhid, dengan cakap belum datang, semoga Allah meridhai bumi. Universitas Islam Indonesia, padamu kami berjanji, majukan studi, giatkan bakti untuk pembangunan pertiwi, syariat Islam amalan kita, tegakkan iman dan tauhid, dengan cakap belum datang, semoga Allah meridhai bumi. Universitas Islam Indonesia, padamu kami berjanji, majukan studi, giatkan bakti untuk pembangunan pertiwi, syariat Islam amalan kita,
morning, Prof. Jiban. Good morning, Prof. Soga. Hello. Hello, Suresh.
Yes, yes, yes. I can hear you, Fatima.
Yeah, how are you? Fine.
Yeah, fine.
Professor Fatima, today morning, first speaker is a Professor Suga or Tofael?
Soga.
Suga.
Suga,
Yeah.
yes, okay, okay. Thank you.
Prof. Soga first, yes.
Yes, yes, thank you.
Syariat Islam amalan kita, tegakkan iman dan tauhid dengan cakap pedoman nyata. Semoga Allah meridhai
I want to check mic.
Just please.
Can you hear me?
Yes, yes. We can hear you, bro.
No problem.
Yes, no problem.
Oh no. Okay. Thank you.
How are you?
Fine. Thank you.
We are very happy.
Yeah. Me
Suga is with
too.
us. Our new experience, right?
Islam amalan kita, tegakkan iman dan tauhid dengan cakap pedoman nyata. Semoga Allah meridhai
Fatima, Professor Fatima, this is the national anthem of
Pardon?
the music actually. This is the national anthem or anything?
No, no, this is the hymn of our university.
Okay, okay.
The hymn of our university.
Okay, okay. Thank you. Thank you. Thank you. Very nice.
Thank you.
Fatima, can we start? Start now?
Yeah, just wait because the admin will admit all participants. The participants are in the waiting room now, so they
Okay.
will admit first. Okay, just wait.
Okay, okay, okay.
I think 2-3 minutes we can wait because 69 participants now, 70. So
Yeah,
maybe,
yeah.
2-3 minutes or just the music is good that your university.
Hello, everybody. Very good morning. Alhamdulillahirabbil alamin. Thanks goodness for our health and time. So today we will can meet again in the international virtual conference of Advanced Functional Nanomaterial and Their Application 2020, which is conducted by jointly organized by Chemistry Department, Universitas Islam Indonesia, NanoCat University Malaya in association with Bangladesh University of Engineering and Technology. So this is the second day of our conference, and for today we'll have 3 keynote speakers. At the first session, we will have the lecture from Professor Tetsuo Saga from Nagoya Institute of Technology, Japan. And then the second keynote speakers will be Dr. Fitria Rahmawati. And the last session is from Prof. Tofel. We can start. We will have the first session with the moderator of Dr. Suresh Sagadevan. So please, Dr. Suresh, to deliver the speakers.
Very good morning to all of you, and warm greetings on behalf of Department of Chemistry, University of Islam Indonesia, and Nanotechnology and Catalysis Research Center, University of Malaya, Malaysia, in association with Department of Physics, Bangladesh University of Engineering and Technology, Bangladesh, are organizing international virtual conference on advanced functional nanomaterials and their application 2020. Welcome back to the second day of ICA FNTA 2020. Let's start the most weighted section of today. For that, I would like to give my artist welcome to our resource person and participant with great joy and immense happiness. It's time that we start our today first section. Let us take up again with our technical section with the resource person, Professor Soga Testo, Nagoya Institute of Technology, Japan. He is going to discuss about the nanomaterial for photovoltaic application. Let us have the pleasure of listening to the honorable and great speaker. I now request Professor Jipan Boda sir to chair the section and introduce the speaker.
Thank you, Dr. Suresh, and good morning to the all participants, my host members, guest speakers, leading scientists, and research scholars, ladies and gentlemen. So we are very happy that in the second day, we have a very good speaker, renowned speaker from Japan, from Ireland. And it's my great pleasure to introduce actually Professor Tetsuo Soga. I know Professor Soga since 2003. So Professor Soga is working as a professor in the Department of Electrical and Mechanical Engineering, Department of the Nagoya Institute of Technology, Japan. Professor Soga has been graduated from the same institute in 1982 and did his PhD in 1987 from Nagoya University. And till today, Professor Soga is adjunct faculty at the University Technology Mara, Anna University, India, Nagoya University College of Medical Technology. And he's working on actually on various materials, carbonaceous materials, nanosynthesis, nanomaterials, and nano devices actually. So his interest is focused on organic, inorganic, hybrid, organic electronics, thin films, and interfacial properties. So far, Professor Soga has published over 600 publications. It's a very good number, and his research gate score is 47. And citations of his publications over 11,000. So it's a great pleasure to introduce Professor Soga. And today already, Dr. Suresh, you mentioned that he will talk about nanoparticles for photovoltaic applications. One more information actually, he's the editor of Nanostructured Materials for Solar Energy Conversion. So I'm very happy to introduce Professor Tetsu Soga to our audience. And we hope that our audience will be very happy and will enjoy his presentation. And again, I would like to thank Professor Soga for accepting our invitation in spite of your busy academic schedule, we know. But our audience, our young researchers, our colleagues, our friends, they will be motivated and inspired with your lecture and presentations. So this is in brief actually what I have mentioned about Professor Soga. He's maybe more than that. So again, I'm very happy to introduce Professor Soga, and our audience will be happy to meet Professor Soga. How are you, Professor Soga, today?
How are you, Professor Poda-san?
I'm very happy that at least to meet you in Zoom meeting. Although we cannot meet physically, but it's a new experience that we are organizing that conference actually. And jointly, these three universities, we are conducting this conference. Professor is Fatima and Dr. Suresh. They are working very hard, and they started to organize this conference. And as a co-organizer, I myself is also very happy to be involved in this conference. I think it's a new experience to all of us during this COVID-19 this situation. So anyway, but it is, I hope the audience will enjoy and this conference. Again, thank you, Professor Soga. Please carry on your presentation.
First, thank you very much for a very good introduction, Poda-san. Today, I'd like to talk about the nanomaterials for photovoltaic application. First of all, I'd like to thank the organizing committee for inviting me to this conference organized by UII, UM, and BUET. First, let me introduce myself briefly. This is a photograph. Actually, I visited Jakarta last year. Not the UII, but the UIN Sunan Kalijaya. And I visited Borobudur temple and enjoyed very much. And last year, I also visited Low-Dimensional Material Research Center, LDMRC, University of Malaya at Kuala Lumpur last year. And I visited BUET. It is a little long back, but I enjoy the BUET and Dhaka city very much. Anyway, let's move to my research presentation. This is the outline of my today's presentation. First, introduction of solar cell. Second, I'll talk about the nanomaterials in organic solar cell, such as zinc oxide nanoparticle, silver-coated zinc oxide nanoparticle, polyethylene glycol, CN carbon nanotube, And third, I'll talk about the nanomaterials in dye-sensitized solar cell, silver nanoparticle, Bi5O7 iodide, nickel tetraphenyl porphyrin, iron oxide nanowire, and so on. And finally, I'll conclude my presentation. As you know, silicon solar cell has been used in the world as a rooftop and also mega solar. Solar cell is clean energy, abundant energy, solar light free, solar light is free, sufficient energy, and so on. This is the efficiency of silicon solar cell plotted as a year. Actually, silicon solar cell was invented in early 1950, and the efficiency was improved. And now the efficiency is around 26. So it is almost efficiency limit. So from now, no further improvement is expected in the conventional silicon solar cell. And silicon solar cell is still very expensive now. So we are studying the organic solar cell. Organic solar cell can be made out of flexible plastic like this, PET film or pen film. So this is very different from the silicon solar cell. So the silicon solar organic solar cell is low cost due to no vacuum process, flexible and lightweight due to low temperature process. So plastic substrate can be used, and very thin compared to silicon due to large absorption coefficient. So I'll briefly talk about the nanomaterials in organic solar cell. This is the operation principle of organic solar cell. The donor and acceptor is used as a active layer, and holo transport layer and electron transport layers here. And when the light is irradiated, electron hole pair exciton is produced, created, and electron come like here, flows like this, and hole flows like this. So this is a very basic principle of organic solar cell. So to improve the conversion efficiency, it is important to reduce the energy loss. In the energy loss, there are several loss, such as light absorption loss, high energy loss, this is a voltage loss, recombination loss, and so on. So to reduce the energy loss, nanomaterials expected. So this is a very old, but I got interested in nanostructured solar cell, and I edited this book, Nanostructured Materials for Solar Energy Conversion, and it was published in Elsevier in 2006, but and the page number is more than 600. So I started this nanostructure solar cell work from this year. So this is a very brief merit of the nanomaterial and nanostructure. So, for example, there are several kinds of nanomaterial, such as semiconductor nanoparticle, metal nanoparticle, metal coated semiconductor nanoparticle, molecule, small molecule of polymers, and nanocarbon, and so on. There are several kinds of material. And this nanomaterial and also nanostructure are expected to improve optical and electrical properties of semiconductor films, results in the improvement of solar cell performance. So, for example, IPC become increase, and the spectral response become broader, and also by changing the LUMO and HOMO level, we can tune the open circuit voltage of the solar cell. So first, I started the carbon nanotube in solar cell because there are a lot of merit of CNT, flexible, strong, and so on. And first, I made this kind of solar cell on the silicon substrate, okay, CNT plus P3OT, and also without CNT was compared. So, and this result, when there's with CNT, the solar cell performance was very much improved compared with a pristine cell. A pristine cell means without CNT. This was published more than 10 years ago. It was explained by using the energy band diagram of carbon nanotube and silicon substrate, silicon. But it was the combination with the silicon substrate. So I moved to the organic solar cell on glass substrate. So recently we are studying this kind of solar cell on the ITO coated glass substrate, P.PSS, whole transport layer, and P3HT PCBM active layer, and aluminum. This is a very fundamental structure in my lab. The fabrication was done by the spin coating, except the aluminum evaporation. Yeah. The detail condition is like this. So all the experiment was done in nitrogen glove box. So I'll talk on the effects of nanomaterials in organic solar cell. So I mentioned that donor and acceptor used in the active layer. So normally it is mixed. So the in the active layer becomes like this. it is mixed of donor and acceptor randomly. It is called bulk heterojunction organic solar cell. So if another nanomaterial is doped, what happens? So the final structure is different. Depends on the properties of nanomaterials. For example, inorganic particle and if the surface energy is similar to donor and acceptor, the final structure is become like this. And if the surface energy of is high, surface energy of nanomaterial high, final structure becomes like this. And if the surface energy of nanomaterial is low, the final structure become like this. So we can control the structure of final structure to some extent. So first I dope the zinc oxide nanoparticle in the active layer. So ITO glass, P.PSS, and P3HP, PCBM, and zinc oxide nanoparticle was added. Diameter is from 20 to 50 nanometer. From the photograph, we can see small particle. It is an agglomerated zinc oxide nanoparticle. This is a solar cell performance for as a function of zinc oxide zinc oxide. So you can see that short circuit current, open circuit voltage, fill factor, power conversion, all the parameters increase with increasing the zinc oxide, like this. It is like that. So now at present, we don't know the exact reason for the improvement, but I assume that it is due to the light scattering effect and also the improvement mobility. This result will show you later. Next, I use silver coated zinc oxide nanoparticle in the active layer of organic solar cell. So in the active layer, P3HT, PCBM, and zinc oxide silver added. This is an example of zinc oxide nanoparticle and the EDX analysis data. So this is spectral response of the solar cell. It is very difficult to see the normal without normal structure, and with zinc oxide, it is almost same. But with doping silver, the peak shift a little bit towards the short wavelength side. I feel this effect is due to the localized surface plasma resonance. So as a plasma effect, there are two. One is localized surface plasma resonance. It is optical absorption is enhanced by the electric field near the surface. And another one is the plasma-induced charge separation. It is a charge separation at the metal nanoparticle semiconductor interface. So I measure the impedance with changing the frequency as a plot. but it is a little complicated. So from this plot, we can estimate the resistance R1 and 2, assuming that the solar cell is equivalent circuit is like this. So as you can see, R1 is this is normal without incorporating zinc oxide nor silver. So with doping, resistance decrease. And from the here, this R2 is decreased. And the decrease reaction is a little different. R2 and R3, R1 and R2. So, and from this curve, we can estimate the mobility. From the here, we can see mobility improves with zinc oxide, and also with zinc oxide silver nanoparticle more increased. So I move to the polyethylene glycol in organic solar cell. It is already very known that TiOx acts as a very good passive buffer layer of organic solar cell. For example, this without TiOx layer. This is TiOx layer with TiOx layer. So this is our result. So with TiOx, the open stack voltage is improved, and also the this is degradation data. So lifetime is improved by the TiOx layer. But formation TiOx layer is difficult because we must make one more layer, another layer. So it is suggested that another layer is incorporated in the active layer, and if it is formed during the spin coating, it is very good. So it is a very simple approach using self-organized buffer layer. So I did this experiment. Structure is almost the same as previous structure, but the polyethylene glycol was added as instead of zinc oxide, and it changed the we did many experiments changing the molecular weight, annealing, and also the content of PEG. But today I'll show the result of effect of amount. This is a solar cell IV characteristic for different amount of polyethylene glycol without PEG and with PEG for different amount. So it plotted short side current, open stacked voltage, fill factor, and the efficiency. The plotted like this. So first, fill factor improves gradually, we can say, and open stacked voltage, it is constant, not a change. And short circuit current first increase and then decrease. Yeah. So the totally power conversion efficiency first increase and then a little decrease. So I characterize the cross section of the sample to see what happens. This is a SEM image. It's not so clear. So this is enlarged one. So here there is one layer around here. This is the PEG layer. Without PEG, this layer is not observed. With PEG, another layer is observed. So it is concluded PEG is formed under the active layer due to the high surface energy by the self-organization. So this is explained by schematically like this. It's without PEG, small amount of PEG, a large amount of PEG. So with the increase of PEG, PEG thickness is increased. So too much thickness degrades the short circuit current. So there's an optimum thickness in the PEG. So this stability of organic solar cell with and without PEG. So compared to with PEG, without PEG, the stability was improved like this. So this is maybe due to the diffusion of water was suppressed by PEG, but suppressed by PEG. So next, I talk on the nanomaterials in dye-sensitized solar cell. So dye-sensitized solar cell, I think you know, the structure is like this. Glass substrate, TCO, transparent conducting oxide, TiO2, and dye. And normally there's electrolyte liquid here, and a counter electrode here. So we did similar, use the similar zinc silver nanoparticle in dye-sensitized solar cell. So here I briefly introduce synthesis of silver nanoparticle. It's a very simple technique. Silver night AgNO solution, the extract of the flower was added and stirred and hold only this. So we can get the silver nanoparticle formed. But by changing the condition, we can make several type of silver nanoparticle. Also, for example, today there's no time to explain detail, but by changing the condition and here or here, very large and not so large. That's very small, and this is large. We can get a different type of silver nanoparticle. And not only silver nanoparticle, we can get gold nanoparticle also by the similar technique. So this is spectra absorption spectra of silver nanoparticle. The peak wavelength is around 470 nanometer, and so around here. And this is a XRD pattern. So it's very crystalline film. So this is absorption spectra of without and with and without silver nanoparticle, and also with and without dye. So you can see, for example, this green curve is only dye. So compared to only dye, with adding silver nanoparticle, the absorption increase a little bit. So, and silver is added more increase. Also, this RB characteristic and solar cell performance for different amount of silver nanoparticle. But so the optimum amount the solar cell performance, such as short circuit current, power conversion efficiency, and offside voltage is increased. This improvement is due to the plasmonic effect of silver nanoparticles. So next topic is TiO2 based nanocomposite material in DSSC. In this experiment, Bi5O7I nanoparticles were mixed in TiO2 nanocomposite to make nanocomposite for solar cell. So by using the nanocomposite, it increase the charge collection efficiency and the charge transport efficiency enhancement, and also suppressing the recombination. This is a little bit complicated. So the TiO2 P25 and BiOI was mixed together and make paste, and it make film with the braid coating, the Dr. braid, and anneal at 450 degrees C in air. So this is a XRD pattern for different bismuth oxide iodide. So with the increase of bismuth oxide iodide, bismuth oxide iodide peak is increased like this. So it means film is a crystallized film. This surface morphology. It is a very small particle is TiO2, and a little large particle is bismuth oxide iodide. So the band gap energy of bismuth oxide iodide is around 2.6 electron volt, and the band gap of TiO2 is around 3.1 electron volt. So by changing the amount, we can change gradually from 3.1 to 2.6 by changing the amount of bismuth oxide iodide. So this is a solar cell performance. It's not difficult to see. The black one is only TiO2. So, and from the here, open circuit voltage is almost same for different bismuth oxide, but current, short circuit current change with bismuth oxide iodide content. This change was explained by this energy band diagram. This is TiO2 energy position, and this is bismuth oxide position, and here is a N719 dye. So from this diagram, we can explain this behavior. For detail is written in published in this paper. So there's a little still some time. So I'll briefly talk about the nickel tetraphenyl propene doping effect in zinc oxide-based flexible DSSC. So we'll skip a little bit faster. This without doping, 0.7% doping, 2% doping, the surface morphology becomes bad. And this is a XRD pattern for different nickel tetraphenyl propene doping. Only compared to the zinc oxide, another peak appears with increasing the nickel tetraphenyl propylene content. So the small improvement was achieved by the nickel tetraphenyl propylene doping. It's a short circuit current, and it's an open circuit voltage fill factor. Open circuit voltage is it's slightly increased, but it's almost the same. And fill factor is almost the same, constant, not to change. But short circuit current increased and then decreased. So this is explained by this energy by diagram. It says that the back transfer was suppressed by the nickel tetraphenyl doping. So finally, I'll talk a little bit about nanostructures in dye-sensitized solar cell. Usually in the dye-sensitized solar cell, TiO2 nanoparticle or mesoporous TiO2 is used. But another structure is like, for example, nanoflake or nanomaya, the possible candidate. In this experiment, iron foil was oxidized for different conditions. When the condition change, iron oxide nanoflake or nanowire or iron oxide thin film were synthesized, and then we made DSSC. This is a SEM and TM image. For example, at 450, surface is like this, and TM image is like this. It's a nanoflake, and 550 degrees C, it is that TM image is like this. Please, this like needle. This is a iron oxide nanowire. And this is a flat film. Yeah, so we can change the shape of the structure. So we made a solar cell by using these three structures. And the solar cell performance is like this. In the case of thin film, the solar cell performance is very bad. But nanoflake is improved, and by using nanowire, more improved. This is improvement is due to the the increase of surface area of the materials. So this is a conclusion of my presentation. So first, advantage of nanomaterials in organic solar cell and DSSC was mentioned. Zinc oxide nanoparticle and silver doped zinc oxide nanoparticle improved the photovoltaic properties. P3H PCBM organic solar cell. A PEG layer was formed under the active layer by spontaneous phase separation and improved the solar cell performance. Bi3O7I nanoparticle and nickel tetraphenyl propylene improved the property of the DSSC. Nanowire structure is suitable compared with nanoflake for DSSC. So this acknowledgement, this work was a collaborative work with Dr. Kishi and Dr. Kato of NITEC, Yasser from Egypt, Dr. Saravanan from India, and Dr. Shamimul Chaudhary, Bangladesh, Dr. Nurhan Rashid, Malaysia, and Dr. Anissa Putri, Indonesia, and Dr. Katori from Nepal, and also many Japanese students, especially Mr. Escato and Arcato. So thank you very much for your kind attention. So this is online meeting, but if possible, I want to see you all face to face in near future. Thank you very much.
Your microphone is still off, Prof. Jiban.
Yeah, thank you, Professor Tetsusoga, for your beautiful presentations. We have actually almost 164 participants are attending your presentations, and that was very beautiful slides also. So now our session is actually for discussion. So many questions from the audience I have. So I think we can get relaxed and discuss actually very friendly actually. Some questions about Dr. Muhammad Kamruzzaman. Kamruzzaman actually, he's from Bangladesh, Begum Rokeya University. So he expressed, this is an excellent talk on solar cells, which is the most important topic in 2021. Thanks, Professor, for your outstanding talk. I'm very much impressed and interested in solar cell research. My question is, what are the main problems to develop nanowires and quantum dots synthesized based solar cell for commercialization photovoltaic market? Is it okay, actually, Professor Soga?
Yes. Are you asking about the commercialization?
Yes, yes, about the nanowires and quantum dots synthesize the based solar cell. So for commercialization photovoltaic market, what is the importance of that nanowires, quantum dots? And it is well known that actually quantum dot shows multiple excitation. So it can generate more photoconversion efficiency. But why we do not so much interested in actually that quantum synthesize, actually, that dye-sensitized?
Yeah, actually now organic solar cell is a stage of fundamental research.
Okay.
So the power conversion efficiency is still low compared with silicon.
Okay.
So first, it is expected to improve the solar cell performance to the level of silicon solar cell, and then we must think the commercialization.
Okay, okay. Yeah, thank you. That second question, actually, Devai, I want to ask, can we get an IV curve without a cathode in organic solar cell? Can you please explain how to make the cathode aluminum?
Aluminum is on vacuum evaporation.
That question is actually how we can get an IV curve without a cathode in organic solar cell.
So you're asking about how to deposit aluminum?
Yeah. How to make the cathode aluminum?
It is done by vacuum evaporation.
Vacuum evaporation. Okay. Yeah, thank you very much. Then one more question. Hello, my name is Vinny. I would like to ask about the fabrication process. Is the inert atmosphere essential to obtain a fine material product due to nitrogen gas globe box?
Yeah.
The inert atmosphere is actually essential for fabrication process.
Some researchers make organic solar cell without nitrogen box. Normal air is okay, but maybe a little solar cell performance is become worse.
Okay.
But we can make anyway. We can make cell.
Thank you, Professor Soga. Kamal Uddin from Bangladesh, maybe. Thanks to the organizer to Advanced Functional Nanomaterials and their Applications Conference. It is a nice platform of scientific community working in the field of nanomaterials and nanotechnology. I am really enjoying the second day of the second day's conference. Okay, thank you very much. Rajakani, how to calculate the mobility? She asked actually how to calculate the mobility.
Yeah, I calculate mobility from the core impedance.
Okay.
I don't know it is correct or not, but anyway, we can calculate the mobility from that plot. It is well known technique.
Yeah. That and again, actually, Professor Kamaluddin, thanks Professor Tesosoga for his interesting delivery. Syed Mohammad Kamaluddin, University of Malaya, Malaysia. Okay. Then Salamat Siang, one more questions actually. Why did you take the that is the silver actually from the nature? What is the XRD of titanium dioxide plus silver?
Yeah, why use silver? Silver is the most common material as a
Okay.
plasmonic effect.
And thank you for presentation, Mr. Soga. Thank you, Professor. Thank you for your presentation, Soga. So we have a very good audience. Last, maybe thank you for your nice presentation, Professor. My question is the presence of iron foil underneath of ferric oxide nanowire may occurs electrical short circuit when they are utilized in DSSC dye-synthesized solar cells devices.
Iron oxide.
Yeah.
We can change the structure of
Okay.
by very easily. Nanoflake, nanowire, thin film, we can change. So I made the solar cell, but maybe it's not so good material for dye-sensitized solar cell. I think TiO2 is more better material.
Okay. So Afrina Sharmin, thanks a lot to Professor Soga. It's a nice talk indeed. Dr. Muhammad Samirullah is also giving you thanks for your nice presentation. Mujibul Haq Babu, actually, he wants to know, you mentioned the band gap declines significantly after the BI507 doping, bismuth oxide doping. Could you explain why?
Why? Why it's due to the band gap of bismuth oxide is smaller than that of TiO2.
Okay. That is the reason actually. Yeah. Thank you very much. Actually, difficult want to make an. What is the difficulties when we want to make a nanomaterial? That Tari Wardani asking about actually what is the difficulties when we want to make nanomaterial?
Difficulty.
I don't know that the question, the difficulties regarding the manufacturing of nanomaterial.
It is still not control of size control is still not difficult now. The variation.
Okay.
Size.
That was very interesting talk actually. That's why so many questions from the audience. That one question, Muhammad Al Mamun. I am Muhammad Al Mamun, a PhD student, NanoCat, University of Malaya. Thank you for your presentation. I would like to ask a general question. That is, the dye-synthesized solar cell can beat the silicon technology in future? It's a very interesting question. Whether this the silicon technology that the dye-synthesized solar cell can beat that the silicon technology. It's a long debate.
Yeah, power conversion efficiency of DSSC is still low. It is about 13% or so now. So it is still half of silicon.
Okay.
Silicon efficiency is about 26% around. So it's almost half. So another new idea is required to improve the performance of DSSC.
Okay. That one question, that is the last actually. What is the nanoparticle size of titanium dioxide doping with the silver?
I use a P25. Now I don't remember the exact size, but P25, if you search, you can find.
And one question to Professor Soga. I am a PhD student from the University of Philippines. In Diliman, I would like to ask what is the optimum thickness of the deposited active layers?
Yeah, it's a very good question. Too thick is not good. Too thin is not good. Yeah, it's about 100 nanometer or so around, or less.
Yeah, that is the good enough for the efficiency, that 100 nanometer.
No, yeah.
Okay, that's all actually. Now we have what is the efficiency of dye-synthesized solar cells? The current state of art actually. One Rajan is asking actually what is the efficiency of dye-synthesized solar cell?
No, in my lab.
Yeah, in your lab or in international?
In my lab, around 80%, but in the world, about 13%.
13%. Thank you, actually, Professor Desosoga, for your nice presentation. And this is the first time we are conducting the virtual international conference. We cannot meet physically, but we can meet our friends from different countries. Those are working very hard and contributing their work in such a So we are very happy to have speakers from different countries. And today's conference is enjoying actually by our audience. Again, I want to thank Professor Soga for accepting our invitation and to give your beautiful presentation to our audience, and hope our audience, our participants, they are enjoying this virtual conference. And definitely we hope to meet physically in near future when everything will become normal and we get our normal life. So thank you and we wish you all the best. And thank you, Professor Soga, for your beautiful presentation again.
Thank you, Prof. Jipan sir.
Thank you very much.
On behalf of ICA FNT 2020, once again, thank you very much, Professor Soga, for your excellent presentation. Your section was full of passion and priceless knowledge. That was really an extraordinary speech. Your section was full of enthusiasm and valuable knowledge. Thank you, sir. It was a spectacular section by you. It was a pleasure of listening to you. I hope that the participant can learn more about nanomaterial for photovoltaic application through your presentation. Once again, thank you so much for your great support and accepting our invitation. Very happy to have future collaboration with your people. Thank you.
Okay, thank you very much, Dr. Suresh, Prof. Jiban, and also Prof. Desosoga. So we have finished the first session for today. And as the appreciation for Professor Soga, we, as the committee, send the certificate for the appreciation. Also to Professor Dr. Jiban as the moderator for today. Okay, ladies and gentlemen, after this, we still have two next speakers, but before this, we will have a break, and the second session will be started at 13:30 Jakarta time. And before you join again with the session, so please fulfill the evaluation form for this conference by clicking this address bit.ly evaluation AFNTA 2020. Okay, thank you very much, and we will start again at 13:30 Jakarta time. See you then.
So can I leave now, Fatima?
Yes, yes, you can leave. You can leave and join again at 30:30.
Okay, okay, Prof. Jipan sir and Prof.
Thank
Hello,
you very
Dr.
much,
Shleshi.
Okay.
Fatima and Dr. Suresh. For you.
Hello, madam. Can you give the evaluation link again, please?
Okay.
Hello, Dr. Shleshi.
Yeah.
Thank you very much.
Professor Oni is there. Yeah, yes. Thank you.
Yes.
Thank
He's very active person.
Yeah, yeah. It's really from the morning. Was in very close to our meeting.
Yes.
We are very happy actually to have you all in this conference. Again,
Again, yeah, 1:30. 1:30.
1:30 is Jakarta time. Yeah.
Jakarta time. Yes.
Thank you very much. Yeah.
Yeah. Thank you. Thank you, Prof.
majukan studi, giatkan bakti untuk pembangunan pertiwi. Syariat Islam amalan kita, tegakkan iman dan tauhid dengan cakap Universitas Islam Indonesia, padamu kami berjanji, majukan studi, giatkan bakti untuk pembangunan pertiwi. Syariat Islam amalan kita, tegakkan iman dan tauhid, dengan cakap pedoman nyata. Semoga Allah meridhoi Universitas Islam Indonesia, padamu kami berjanji, majukan studi, giatkan bakti
Aneng di
pembangunan pertiwi. Syariat Islam amalan kita, tegakkan iman dan tauhid, dengan cakap pedoman nyata. Semoga Allah meridhoi
صار لهم داخل المجمع الصحي ولاد.
Halo Bu Fitria. Halo Prof. Jiban.
Yeah, hello.
Halo Budis. Assalamualaikum.
Have a good break.
Yeah.
Baik, Mbak Fitri.
Halo.
Assalamualaikum warahmatullahi wabarakatuh. Good day, everyone. Welcome again to the screen. We will have the second session of the International Virtual Conference of Advanced Functional Nanomaterial and their Application. And for this session, has been joining with us Dr. Fitria Rahmawati from Universitas Negeri 11 Maret, Surakarta, Indonesia. She will give the topic about the zirconia-based material. Shortly, I will read about her curriculum vitae. Dr. Fitria Rahmawati was graduated from Institut Teknologi Bandung, Indonesia, and is joined with the chemistry department Universitas Negeri 11 Maret. Her research focus are related with the zirconia material, graphene and graphene oxide, as well as other solid state material for photocatalysis, catalysis, and energy application. And some of the interesting published paper, for example, in 2019, she published in Journal of Dispersion Science and Technology, entitled The Preparation of Yttria Stabilized Zirconia Film from Aqueous Nano Grain Suspension for Solid Electrolyte. And then in the Journal of Material Research and Technology in 2019, with the title of Yttria Stabilized Zirconia Film Produced from the Aqueous Nano YSZ slurry Preparation and Characterization. And there are many, I think it is more than 40 related international journal publication with related topic with she will give in this lecture. So thank you very much, Dr. Fitria, for kind sharing and accepting our invitation to join with this conference. So please give your lecture.
Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Let me share my screen. Have you seen my screen?
Yes, yes.
Okay. Yes. Thank you very much to all of the organizing committee, Professor Isfatimah, Dr. Suresh Sardevan from University of Malaya, and also Professor Jiban Boder from Bangladesh University of Engineering and Technology for inviting me to this prestigious event, the Advanced Functional Nanomaterial and Day Application. Thank you very much for inviting me. Yes, today I'm going to talk about zirconia-based material for solid electrolytes. I'm coming from Chemistry Department, Universitas 11 Maret, located at Surakarta, Indonesia. Surakarta is a city in Central Java, near Yogyakarta, where Professor Isfatimah is living. Yes, and I'm working on the solid state chemistry and catalysis group. For introduction, as we know that we are now facing global warming effect that causing some problems such as drought and flood and also melting of polar ice caps. And because of the greenhouse gases emission, such as CO2 emission, we graphite that the emission of CO2 increasing year by year, and the increasing became so high after industrial revolution started. Therefore, we have to find some way to reduce the CO2 emissions, such as by replacing the use of fossil fuel with the cleaner fuel like hydrogen, or because of the emission of fossil fuel itself. I think we have to start to replace the use of fossil fuel with some kind of biofuel. And also we have to find new and renewable energy resources such as solar lights and also wind power and hydropower. But beside of that, we also have to think about the technology to produce the energy itself, the technology that may emit lower carbon emission or even zero carbon emission. And because of the new and renewable energy usually less sustained than the fossil fuel itself, we also have to think about the energy storage technology. And this part, electrochemical cell may be one of the alternative solutions, because this electrochemical cell can convert chemicals into electrical energy directly. Meanwhile, if we use combustion engine, the chemical will be converted into heat, and then heat move the turbine and then producing electric. So because the conversion can be directly happened, the electrochemical cell can have higher efficiency than the combustion engine. Why it has higher efficiency? It's also because the more specific reactions occur within the electrochemical cell compared to the combustion engine, of course. Therefore, we can expect that the carbon emission or other pollutant gases emission will be lower than if we use combustion engine. Other advantages are like more flexible design, and then more quiet and less vibration, and also less than zero emission. The electrochemical cell that is operated by flowing fuel named as fuel cell. As we can see in the scheme here, there are 4 main parts in this fuel cell. the anode part, and then cathode, electrolyte, and external liquid and an external circuit. To operate this fuel cell, we flow the fuel. For example, if we use hydrogen gas as fuel, we flow the fuel into the anode part and then use oxygen in the air as the reducing agent, flowed into the cathode part. When the oxygen molecule reach the cathode part, the oxygen molecule will be reduced into oxygen ion, O2-, and then the oxygen ion migrate through the electrolyte, reach to the anode part, meet with the hydrogen molecule, and then conducting oxidation reaction that release electron, and then electron coming into external circuit to load something, and then coming back into the cathode part to be used as the reducing agent again. As you can see in this reaction, the total reaction will be hydrogen plus oxygen, and the production will be water molecule. So if we use hydrogen gas as fuel, there will be no carbon emission at all. There are many kinds of fuel cell. However, in my lab, we are focusing on solid oxide fuel cell because of many reasons. The first one is flexible choice of fuel. Still we can use the fossil fuel or hydrocarbon fuel, and also we can use biofuel, and of course we can use hydrogen gas as fuel also. Why? Because there is no catalyst inside the solid oxide fuel cell. Therefore, there is no considering about poisoning catalyst that caused by fuel choices. And this solid oxide fuel cell also provide high power density. Therefore, this kind of fuel cell is a good choice for electrical power plant. And until recently, the development of SOFC or solid oxide fuel cell directed to decrease the operational temperature for 300 until 600 Celsius, because usually SOFC is operated under 800 up to 1000 Celsius. And those are many topics that we have conducted within the SOFC research. The zirconia preparation from the local zircon trend. Actually, I was conducted this zirconia preparation from local zircon sands since I was in my doctoral degree in ITB, and it continues until now. And then conducting yttrium and calcium doping into the zirconium oxide, and then making composite of the yttrium stabilized zirconia with the lanthanum galate structure compound, and making a composite of YSC with samarium dockeria, and then the production of nickel YSC for anode material. And then recently we also prepare aqueous nano YSC slurry. For battery itself, this battery also electrochemical cell that has four main part also: the anode, cathode, electrolyte, and then external circuits. And what we are conducting in our lab is including for lithium-ion battery, sodium-ion battery, and solid-state lithium-ion battery. These are some topics to get the battery. Yes, we are preparing material for sodium-ion battery cathode by dope Mn into sodium peroxide. The sodium peroxide itself was prepared from the commercial iron oxide, and the iron oxide that was prepared from our local iron sand. Conducting electrochemical sodiation to sodium iron phosphate. This is also for SiB cathode. And then we also investigate material for anode carbon from biomass for lithium-ion battery and also for sodium-ion battery, and making a composite of graphite with lithium zirconate for lithium periphosphate battery energy. And we also conducting research on material for electrolyte. This year we are focusing on lithium lanthanum zirconate based material, because this year we have funding from a company to conducting this research. We prepare the lithium lanthanum zirconate from our local zircon sand and compare the result with the commercial one, and also conducting doping boron and aluminum, and also titanium and aluminum with a single doping or double doping. Why the company giving me a funding for that all solid state battery? Because we know that the development research on the battery is moving from traditional battery, which use liquid electrolyte, to the all solid state battery that use solid electrolyte. Because if we use solid electrolyte, the safety will be increased because there's no possibility of liquid leakage. Also the design can be more flexible, and also the battery can be lighter than the traditional one. This is the material for solid electrolyte. The left one is for fuel cell, solid oxide fuel cell, I mean, and the right one is for all solid state battery. As we can see here, that zirconia-based material has sufficient ionic conductivity, even though the value is still lower than the lanthanum colored compound or sodium oxide-based material. However, it is known that zirconia-based material shows better stability than sodium oxide-based or whether the lanthanum colored-based. And therefore, this is still interesting to be investigated more. And for solid-state battery, the lithium lanthanum zirconate is within the second generation in here. Yes, the ionic conductivity also sufficient to be chosen as the solid electrolyte as for battery, even though the ionic conductivity is still lower than the newest generation one. However, the cubic garnet of lithium lanthanum zirconate is still very interesting to be investigated because of the high stability. Consideration on choosing of zirconia-based material for solid electrolyte, whether for fuel cell or for battery, we have to think about if we want to choose a material for solid electrolyte for fuel cell, we have to be sure that this material can be a good medium for oxygen ion migration, And then if we want to choose a material for solid electrolyte for battery, as for example, for lithium ion battery, then we have to be sure that the material can be a good medium for lithium ion transportation. This work has been conducted in our lab, the zirconia synthesized from zircon sand by caustic fusion method, and then produce this powder, this zirconia powder, and then we compare the result with the commercial zirconia powder. And this was procured from China. And after conducting analysis, the XRF analysis, we found that actually the prepared zirconia has zirconium content relatively similar with the commercial ones. And also the kind of impurities inside the prepared zirconia also almost similar. So probably the commercial zirconia also was produced by caustic fusion or similar method with conducted in our lab. And then we analyzed the powder with XRD. We found this diffraction pattern, different pattern with the commercial zirconia, And then after conducting label refinement, we found that the commercial zirconia is crystallized within one phase of monoclinic structure. Meanwhile, our prepared zirconia available within two phases of monoclinic and tetragonal, in which the tetragonal dominate the structure. Even to theoretically, the transformation of monoclinic zirconia into tetragonal zirconia usually occur at a high temperature over than 1000 Celsius. However, there are also another researcher that found the zirconia formed within a tetragonal structure only by heating at 800 Celsius. This one is in agreement with our result. And also another researcher found that the reversible transformation from monoclinic into tetragonal was also happen under calcination temperature below 1170 Celsius. This is also in agreement with our result. And then we are conducting yttrium doping into zirconia. We are conducting compositing of zirconia-based material with lanthanum colored structure. And we found that when we add LSGM compound into the calcia yttria zirconia, we found that the secondary phases started to present it. The secondary phases are lanthanum strontium oxide and then lanthanum strontium gallium oxide and also lanthanum zirconate. The cases also happen when we add LSGM into the yttrium stabilized zirconia. More LSGM added into the zirconia-based material, the secondary phases available more. And then by measuring the impedance of the material, we found that, and then calculate the ionic conductivity from the impedance data, we found that actually the addition of LSGM did not contribute more into the increasing of ionic conductivity. As you can see here, this one is CYZ, the single, and then this one is the composite with the LSGM. And even the addition of LSGM into the YSG decreased the ionic conductivity of the material. However, we can see here at high temperature, the ionic conductivity of the CYZL can increase a little bit, only a little bit, because yes, it can be seen in the impedance curve in here, that when we increase the temperature to 50 degrees Celsius, the impedance of the composite decrease until lower the single phase of CYZ. Why the addition of lanthanum galate compound does not contribute more to the ionic conductivity of the YSC or as well CYZ, because it can be seen in here that there are some blocking phase like this that described in this image, SEM image, and then we try to analyze this blocking phase part, and we found that this part is an area with the silica rich. So this is a silica rich blocking phase. So it can be concluded that the addition of lanthanum galate, especially the 10% of lanthanum galate, can force out the silica from the bulk phases and then aggregate into larger grains, but they only distribute in to the some definite places. And the presence of that blocking phase seem to inhibit the increasing of ionic conductivity, because actually when we add 10% of LHM, actually the grain boundary can connect very well. The grain can connect very well after we add 10% of LSGM in here. So actually, this can increase the ionic conductivity value, but the presence of blocking phases may inhibit the further increasing of the ionic conductivity. So actually, if we use the very pure or high purity of zirconia, maybe the result will be better than this result. About the ability of LSGM to increase the connection between grain also can be analyzed from this result. This is the Arrhenius plot of the ionic conductivity. As we can see here, that when CYZ single, the grain boundary conductivity is lower than the grain conductivity, and after submit 10% of LSGM, the grain boundary conductivity become comparable with the grain conductivity. So it means that the grain boundary conductivity is become better. And then next work is preparing aqueous nano YZ slurry. The YZ slurry actually has been commercialized. However, usually the production use organic solvent to prepare the YZ slurry. And in this investigation, we try to change the organic solvent with distilled water, and use two types of dispersion, the alpha terpineol and surfactant. Yes, we add the surfactant here, the blend of trin 80 and span 60. There are two kinds of slurry that we have made. The first one is with the surfactant blend, and then the second one is without surfactant blend. Before we start to make the slurry, of course, we must reduce the particle size of the zirconia and yttrium oxide to be nanoparticle before reacted them to produce the YZ. And we reduce the particle size by conducting this destruction with sodium hydroxide destruction, and then autoclave in 150 Celsius for 24 hours, and then conducting centrifugation, and then decantation, followed by acid leaching, and followed by water leaching, and then drying, and then calcination at 1000 Celsius. And at the other side, we also find the required HLB. HLB is hydrophilic lipophilic balance. The required HLB means the HLB value that has the best stability for the YZ suspension. So in order to find the HLB, the required HLB, we variate number of HLB by combining twin 20 and span 60 by using this formula. X is the targeted HLB, and we make 8 different HLB YZ suspension, and then observe the suspension from the first day until the 7 days, and we found that the suspension with surfactant blend of HLB10 has the highest stability in here. Therefore, for making the YZ slurry, we use the formula of surfactant blend to produce the HLB10, to make a formula in here by this composition. And then, as we can see in here, then the slurry A producing the queen tape. Yeah, producing the queen tape like this, and then this is the film after drying at room temperature. This is also the queen tape from slurry B, and this is after drying at room temperature. And And it seems like the ZnO tape soon become wet after stored at room temperature. Meanwhile, the B tape is keep drying for many days. Therefore, for further analysis, we only can direct to the B tape. This is the surface morphology and the side SEM image. And this one is the FTIR of the green YZ tape. You can see here there is a peak at 563, indicate the presence of vibration of ZnY and O. And by comparing the study pattern between YZ powder and the YZ tape, we can see that there is no difference on the experimental pattern. It means that there is no phase change. And impedance analysis to this material found that by increasing the temperature, yes, the impedance value decreased significantly. This one from 500 into 600 decreased significantly, and then 700 Celsius and then 800 Celsius. And after conducting fitting by ZQ and applied RC network model, we found here that at 800 Celsius, the YZ tape can have 3.9 times 10 to minus 3 Siemens per centimeter. This is quite high for solid electrolyte for fuel cell. Even at 600 Celsius, the ionic conductivity is 8.79 times 10 to minus 4. This is also sufficient actually for solid oxide fuel cell. Thermal analysis found that this tape at around 90 to 100 Celsius is indicated as water removing, and then from 100 into 210 is about glycerin and PPA decomposition, and then from 210 up to 670 is about alpha terpinol and polypropylene substrate decomposition, and then remaining the YZ at high temperature, because as we know that theoretically YZ will be decomposed at a very high temperature, maybe up to 2000 Celsius. And another research on preparation of YZ slurry has also been published in this journal, 2019. Yes, we changed the span 60 transfected with SDS, the higher HLB value surfactant. Then we checked the required HLB, and we found that at 26, we got the most stable YZ suspension. And then we make a slurry by following this composition. The A slurry A is with surfactant blend solution, and slurry B is with surfactant blend solution. We can see here in the optical image that the slurry A or YZ tape A with the surfactant blend solution provide very smooth surfaces. Meanwhile, the YZ tape B shows a quite rough surface. Also, when we check with the SEM analysis, the YZ film can be casted very well from slurry A and produce a good film in here, a good YZ film. Meanwhile, when we casted the slurry B onto polypropylene substrate, the slurry seems like run out from the substrate. And this is the particle size distribution of YZ particle. This YSG film A has this has mean particle in 12 nanometer, meanwhile the YSG tip B has the mean particle size about 13 up to 14 nanometer. It means that yes, the presence of surfactant blend solutions seem to take an important role in this slurry preparation. This is the XRD pattern of the YSG film A with surfactant blend and this without surfactant blend. There's no difference in here. And the characteristic peak also is similar with the YSG powder. It just the peaks little bit broad than the YSG powder. It indicates the small particles inside. And then Libel refinement found that the YSG film A and YSG film B was in cubic structure with FN3M or similar structure of zirconia. FTIR analysis shows peak at 563, similar with the YSG that was prepared with via the surfactant blend previously. And this peak indicates the vibration of zirconia, yttria, and oxygen. And then impedance analysis also found that by increasing the temperature, the impedance value reduced significantly in 600 and then 400, 300, 500 and 600. And then we calculate reconducting fitting with the fuel by applying RC network model and calculate the ionic conductivity. We found here that at 600 Celsius, the ionic conductivity of YSG tip P is 2.25 times 10 to minus 4. Meanwhile, the YSG tip are 2.08, so it's a bit lower than the YSG P. However, the quality of the film itself, YSG tip R is better than YSG tip B. Also, we try to investigate the resistance between electrolyte and electrode. Yes, we use the YSG and ES electrolyte, and then we casted NEYSG as electrode, and then we measured the impedance, and we found here that the resistance between electrode and electrolyte at 600 Celsius is around 1,475 ohms. YSG tip R shows higher resistance between electrode and electrode than the YSG tip B. But again, the quality of film YSG tip R is better than YSG tip B. This is the RMU's plot between two tips, and we found here that the activation energy for oxygen ion migration between them actually almost similar, 0.987 and 0.562. And then our work about zirconia-based material for battery. We have conducted material for anode composite and also for solid electrolyte. For anode composite, this was published in Chemical Papers, Springerling. This work was conducted by a master student, and this is about a composite anode of lithium zirconate powder with graphite. For preparing the lithium zirconate powder, we use the zirconium oxide powder with lithium carbonate as precursor, and we mix them at the Paris ratio like this, and then conducting ball milling at 300 RPM for 2 hours, continue to 480 RPM for 2 hours, and then heated at 950 degrees Celsius for 10 hours, and then resulting this kind of powder. And then we conducted, the characterization to this powder. This is the exhibit pattern of the lithium zirconate sample. And this one is some SEM image of the lithium zirconate at a different magnification. And after conducting the refinement, we found that the lithium zirconate was crystallized within monoclinic structure at all of the various ratio of the precursor. And the produced lithium zirconate then was mixed with graphite, and here with the composition as described in this table. Yes, and then we fabricate the battery and then check the battery performance. And we found that we use lithium periphosphate as cathode in this case. And we found the LFPG showing 250 milliampere hour per gram, the specific capacity. And after submitting 20% of weight LiZO to the anode, the specific capacity reduced into up to 184 milliampere hours per gram. Also, when we submitted 30% of LZO into the graphite, the specific capacity is still around 184 milliampere hour per gram. However, when we check the cycle ability of this battery, we can see here that the LFP battery with the single graphite as anode, even though the initial capacity was very high, but the capacity decreased quite rapidly after the second 10 cycle, and then the third 10 cycle. You can see here that it dropped quite fast. However, for LFP battery with 20 LZO G, it means that 20% of LZO submitted into the graphite powder. It shows quite stable under 60 cycling of testing of the performance testing. But the LFP battery with 30 LZO shows also not good performance. We can see here it drops, the performance drops quite fast. And these are the Coulombic efficiency for LFP battery with 20 LZOG. The Coulombic efficiency is good. It's around 95, above 95 up to 10. And this, even though the specific capacity, the initial specific capacity is not too high as the single graphite, but it does not decrease rapidly for 50 cycling operation. And then when we check the cyclic photometry of this battery, we can see here that the current density of LFP battery with 20 LZOG shows the highest current density than two others. It means that actually the reaction rate in the battery when we use the 20 LZOG as anode can occur fastly other than the single graphite as anode. And when we try to compare our result with other result, we found here, this is our result, that actually our initial capacity is quite high compared to the other research. They are also using lithium zirconate base for anode. And then, yes, we use a low current rate, only 0.037. However, this one also use a very low current one, but still we have initial capacity. We have higher initial capacity in here. And the potential it will be in between 3.2 and 3.4. This one is secret photometry curve from the LZO and MCMD. We found here that in LZO there's a peak at 0.63 and 2.2 volts, indicating the lithiation process, and then peak at 108 volt and 2.2 volt indicate the dilation process. If we compare the MCMD, there's a different voltage when the dilation occur and when the dilation occur. This is the reaction to the lithiation and dilation. And this is the impedance analysis of the battery. We can see here that the LFP battery with 20 LZOG has the lowest impedance value, indicating the low internal resistance inside that. Yes, the lowest internal resistance. And when we check the excited pattern at before and after 50 cycles, after operated for 50 cycles, we found that there is no change on this characteristic peak. However, when we zoom on this part, yes, it is also the decrease of intensity occur. And then after conducting Liebherr refinement, we can see here that there is volume change. Volume change at before and after 50 cycles in here. And we see that the submitting of 20% LZO can inhibit the volume shrinkage or volume change, the higher volume change. So it means that the addition of 20 LZO can inhibit the volume change abruptly. And this is a good result. This table can be used to compare the result between the graphite as single anode and then by submitting 20 LZO and 30 LZO. Yes, we can see here the capacity retention for graphite is about 57, and then capacity retention for LFP battery with LZO submission into it quite higher than the graphites, than the single anode of graphite, at about 62 and 66. And then the zirconia-based material for solid electrolyte. For this year, we have also produced some powder by using different raw material, the prepared zirconia and then the commercial zirconia and the very higher purity of zirconia, and we form this powder. And then we make a sintered pellet of lithium lanthanum zirconate. This is the optical image of lithium lanthanum zirconate, and then we make a sintered pellet of them and casted the lithium cobalt oxide on the surface and MCM the slurry on the other surface. And then to increase the interaction between electrode and electrolyte, we press with the core isostatic pressure and then fabricate the battery and check the performance. Yes, we want to make a solid state battery like this, like this one made. And this work is still ongoing, and I cannot share the data today because it's still ongoing, and also this project was funded by a company and it is not finished yet. Also, we have to fabricate by a different method, by casting method. At first, we casted LCO slurry on the CU foil, and then above of it, we casted LLZO slurry. And then after dried, we casted MCM with slurry on it, and then yes, laminated and fabricate the battery like this. Yes. This is also still ongoing, and yes, still we don't have data to be shared. So for conclusion, zirconia is potential material for producing functional material for solid oxide fuel cell and also for battery, whether for energy or electrolyte. And also there are many interesting aspects to be investigated more. I say thank you to my students. They are always with me in my lab, working every day. And also thanks to alumni of my lab. And also thanks to Universitas 11 Maret for providing some research project, for providing funding from research project, and also for Kemenristek Deputy, also for funding some of my research project. And last, thank you to PDMS Pertamina for funding the research projects on solid electrolyte based on lithium lanthanum and zirconia. I think that's all for me. Thank you very much.
Thank you very much for nice and very attractive presentation, Dr. Fitria. I think it is very attractive topic actually. So also we have two questions from the group chat. The first question is coming from Shirley Jolanda Sekewile from Patimura University. Dr. Fitria, do you have any data which is comparing the properties of liquid batteries with the solid one that you have prepared? And the second question is coming from Hamishu Aliyu Muhammad from University Malaya. Is it possible to use metal organic framework as the source of metal oxide? And I believe that the calcination of zirconia MOFs can provide the corresponding oxides that can inherit the porosity of the parent MOF, and it can also allow doping to be made with ease. And do you think the MOF can be a good source for the metal oxide for solid electrolyte?
Oh, yes. Thank you very much for this two kind question. Comparing liquid battery and the solid state battery. Yes, actually, I have checked the liquid battery capacity and also checked the all solid battery that we have prepared in our lab. The specific capacity of our all solid state battery is still very low comparing to the liquid battery one. This is why it is so challenging how to increase the specific capacity of the all solid state battery. Yes, because actually all solid state battery is until recently is still under very dynamic investigation by some researchers all over the world. So that's why the Pertamina very interesting for me to conducting this research, because this is quite a new technology on the battery itself. And then what about MOF as the source material, and as it can be used for solid electrolyte? Yes, there are some research on the use of MOF, whether for electrolyte or for electrode. So some of the research using MOF as the substrate for the metal oxide, and then some of them using as the source of the metal oxide, and the metal oxide as the solid electrolyte for the battery itself. So the answer is very possible to use MOF as the solid electrolyte. Thank you.
Okay, and another question. Actually, there are many, but some question, I think, which phase of zirconia is suitable for the battery? And then if we want to use, coming from Tari Wardani, if we want to use this battery for commercial, is the price is cheaper? Then the similar question coming from Majibul Haq, which phase is very important for zirconia in the application of the battery?
Yes, about the phase of zirconia itself, we have produced the lithium lanthanum zirconate by using the different raw material of zirconia. The first one is our prepared zirconia from zircon sand, which is tetragonal phase dominated. And then the other raw material is the commercial with the similar purity of zirconia, but the phase is monoclinic. And then the other raw material is the very high purity of zirconium oxide with a single monoclinic phase. And we found that the lithium lanthanum zirconate that has been produced from single monoclinic zirconia, providing cubic garnet structure of lithium lanthanum zirconia. So actually still there are two phases within the lithium lanthanum zirconate, the cubic and the monoclinic. However, when we use the tetragonal phase, the monoclinic phases of the lithium lanthanum zirconate higher than the cubic phase is so very low. This is what we get from the refinement, from the refinement. When we use the single phase of monoclinic zirconia, we can have almost 50% of cubic lithium lanthanum zirconate on it. So it means that monoclinic zirconia is better than the tetragonal zirconia for raw material of preparing lithium lanthanum zirconate solid electrolyte. Because until now, it is known that the cubic garnet lithium lanthanum zirconate is still the best solid electrolyte for battery. And then, is it worth it to all solid state? Do you mean worth it with the price?
Yeah, mean that is it possible for commercialization? Something like that?
For commercialization.
Yes.
Yeah, yes, as I said, that actually this all solid state battery is still under dynamic investigation all over the world. But it is very possible to be commercialized as long as we can reduce the cost production. And of course, if the specific capacity of the all solid battery can be comparable with the lithium battery itself. Until now, the highest specific capacity, as I know, is about 120, which is still lower than the than the lithium ion battery with the liquid electrolyte, because the battery with liquid electrolyte can more than 200 milliampere hour per gram. But I believe that in the next we will move to the all solid state battery, because the design can be more flexible. So if in the next there are more electrical vehicles to be fabricated, it is not possible to use the liquid battery because of the some disadvantage provided, such as the possibility of liquid leakage, cause explosion, and also very weight. But all solid state battery can be solution about this. This disadvantage of liquid battery.
Okay. Okay. The question from Hack, I think it is another continuing question from the first question. You mentioned that your sample transformed from monoclinic to cubic phase. Why?
yeah, transformation.
Yes.
It only happen to the solid structure actually.
Mhm.
The zirconia available in this work within monoclinic, tetragonal, and also cubic. It depends on the temperature to synthesize actually. So at low temperature, usually zirconia available within monoclinic structure, and then when we increase the sintering temperature, the structure can transform into tetragonal because of the high temperature can provide energy for the atom inside the structure to reorganize themselves, and that's why they change the structure. Of
So
course,
you mean that in the synthesis, we must optimize the temperature of the sintering, something like that, or
yes,
yeah.
That's,
So have you did the optimization for this?
not yet, still not yet.
Not yet.
Yes, still
Okay.
we have to paste the tetragonal and monoclinic, but in the next we want to force to have a single monoclinic. Like
Okay, so what is in your idea, because you mentioned that in your CV also you use the raw material from the nature as the source of the zirconia. What is the tricky step of the synthesis? Which one?
for process, you mean?
Yeah, yeah. You mean that you mentioned that you use the natural.
Yes.
Yeah. So what is the tricky step in the synthesis?
The aim is to get the high purity of zirconia itself. And I know still we have only about 74% of zirconia content inside with some impurities embedded within. Therefore, in the way to increase the purity of zirconia, I have tried to conduct double filtration. However, double filtration means the water leachings I've conducted twice, but the result still not too satisfied. And then now we are still doing to increase the purity by conducting heating treatment during water leaching. But it's still ongoing.
Okay. The other question, actually, the time is end, but it is I think important question. What are the main finding from Muhammad Nasmuddin Rafat from Hanseo University? What are the main finding of zirconia and what are characteristic difference of the different zirconia? I think you have mentioned, yeah, just mentioned the different properties of monoclinic, cubic, and tetragonal extra. And then, but you said that monoclinic phase is better for battery. So, but your sample belong to the cubic. So, where is the application of your research? I think you also have mentioned it, but just please give brief discussion for this.
Yeah, the main finding is monoclinic zirconia is better one than the tetragonal zirconia to be used as raw material, whether for solid electrolyte for fuel cell or solid electrolyte for all solid state battery. Yes, monoclinic is better than tetragonal one. And then the different characteristics of zirconia. I don't get the next question. It's about
Means that what are the characteristic difference of different phase of zirconia? What is the role of temperature variation? I guess that it is related with the temperature of sintering to make
yes,
a certain phase, something like that.
yes, yes. That depends on the temperature we apply.
Okay.
Yeah.
Okay, and the rest participants are commenting very good presentation, Dr. Fitria,
Thank you.
and thank you very much. I think it is open our mind for potential research in energy sector, I think. So again, thank you very much for Dr. Fitria for your presentation.
Yes, you're welcome.
So yeah.
Thank you very much.
Okay, so as the token appreciation, we also give the certificate to, oh sorry, to Dr. Fitria. It is about to send to your email soon. Okay, and thank you very much. It is the end of the second session with Dr. Fitria Rahmawati from Universitas Negeri 11 Maret. Then we will move to the last question for today with Prof. Tofel AM said, but I'm not sure is the professor joining us. Okay, the moderator will be Dr. Suresh Sagadevan. So please, Dr. Suresh, to deliver your session while we are waiting for Professor Tofel.
Thank you, Professor Fatima.
Yeah, thank you.
Hello.
I don't see that Professor Tofel joining us already.
Yeah, Fatima, actually he is having meeting. So he will join after 30 minutes.
Okay, after 30 minutes. Oh,
Yes,
okay.
yes.
Okay.
Now he have another meeting. Maybe he will join shortly. So we have to wait. Hello?
Yeah.
Yeah.
Is there any discussion from you or from Prof. Jiban to the second speakers, please?
So that Tofel is the last speaker today.
Yes. Yes,
So,
Prof.
yeah.
At present, we have meeting now.
No, he's okay, all right. But we have
Yeah.
another session. Maybe there's some photo and actually, Professor is Fatima mentioned. Maybe there is a one.
Hello,
Because
Dr. Fatima.
we have already 156 participants we have. So that
Yes.
time we can do and just open discussion.
Okay.
We will check it for check.
Yeah, or maybe participants want to ask Dr. Fitria, also welcome. So we wait for 30 minutes?
Another 10 to 20 minutes, yes.
Okay, 10 until 20 minutes, okay.
Yes.
Can I have ask one question to Dr. Fitri? Am I audible? Can I ask?
Yes.
Yes, please, Professor.
Okay, thank you very much, actually. I'm enjoying your presentation and also a lot of questions from the audience. And you answered actually to all the questions and very nicely. Especially actually my concern is in Bangladesh, you know, we have the longest sea beach in the world. So we have that the source zirconium in our beach sand. And it contains around 7-8% is raw beach sand. So we know that the vast application of zirconium, it is a tough and very hard material. So the artificial diamond, what we are using actually, that is the zirconia.
Yes.
And another use is actually as a fuel material for nuclear reactor.
Yes.
The cladding and that the mixing of that, the uranium with the zirconia is a vast application we know actually.
Yeah.
Can you suggest actually from the beach sand, how we can extract actually this zirconia and to purify just in the simple way? If you have any idea, so you can share your experience to the audience so that will be benefited from you.
Yes, I will try
Actually.
to share this on my experience. We also preparing the zirconium oxide powder from zircon sand. Zircon sand is actually the side product of tin mining plant in Indonesia, which are spread over Kepulauan Bangka Belitung and also at Kalimantan. Yes, we also have much abundantly available in Indonesia, the zircon sand. And of course, the zircon sand is still low concentration of zirconium. Therefore, the first step is how to concentrate the zirconium oxide from the zircon. Zircon means ZrSiO4. Yes. And usually conducting caustic fusion by crush the zircon sand with the sodium hydroxide. Yes, and then providing heat treatment at about 800 Celsius. And then after that, we will have fritz. And then from fritz, we can crush again into the powder. And then after that, we made a pellet and then we heat it again at about 1000 Celsius. And after that, then we have the zirconium hydroxide, and zirconium hydroxide changes into the zirconium oxide. But before sinter, we have to leach the crush fritz with the acids. In this case, I use hydrogen chloride solution, and then follow with water leaching in order to neutralize the pH. And then after that, conducting heating treatment again and form the zirconium oxide. So until now, as I said, that still we have the purity up to 74, the highest one, and there are many impurities inside. And it is still ongoing now how to increase the purity of the zirconium oxide. The highest impurities inside actually is sodium. Then sodium coming from the sodium hydroxide that we use to decompose the zirconium silicate into the zirconium hydroxides. And it's still that the heating treatment does not enough to release the sodium. That's why now we try to remove this content of sodium by water leaching, but with heat treatment, and variate the heat treatment, and we try to find what temperature to be the best way to remove the sodium content within the powder itself. So my answer is, if you want to produce or want to use your beach sand, 78% of zirconium content is actually very high. So you just need to decompose the zirconium silicate with the sodium hydroxide, and then following these steps until you find the zirconium oxide.
Thank you very much. In your sample, do you have any thorium in the beach side?
Only not thorium, actually, titanium. Yeah, there's silica, titanium, and magnesium also. But the highest level is sodium, and then silica, and then titanium, and then magnesium. But that's depend on the raw material actually. Probably if the zircon sand from Bangladesh might be different with the zircon sand from Indonesia.
That's true. Actually, we have a both. Actually, the thorium is also there, and
Yeah.
zircon,
Okay.
it's, the rich sand contains the lot amount of the thorium and the zirconium.
That's radioactive. That's radioactive.
So I think we have a very big audience. Can you tell us actually during this the lockdown situation, how you are conducting your research in the university in Malaysia or Indonesia? So the students, you are allowing the students to conduct research in the lab or no? Just
I said, lucky for me that because my home is not so far from my university, so it's still allowed for me to go to my lab to conducting research even though during lockdown situation.
okay. But
If
we know,
I have permission from my dean also with my research.
yeah, so this is very unusual days actually we are passing. So we know that due to that the COVID-19, so normally in our universities also we are conducting the online classes, right? So
Yes,
but
for classes online.
we do not open that the laboratory for free access or easy access to all the students till now. But we are thinking gradually we will open and we'll start our activities. But without research, you know that all scientific communities, so we are waiting for that better days to start our normal activities. So but even then, our audience and number actually participants, we can share our experience, or you can, Dr. Suresh or Dr. Fatima, you can open just for discussions because the 10 minutes we can share our experience among the participants, right? And as we have to wait for Tofel for another 10-15 minutes.
Yes.
Okay, sorry, Dr. Fitria.
Fitria is very wonderful person.
Because I shared the wrong file, so this is the certificate for you.
Oh, thank you very much.
As the second speakers. Okay, I just send you by email. Thank you.
I'm Dr. Suresh Agadevan. I have small questions regarding your presentation. Can you tell us what are the challenging for preparation of zirconia? You are facing challenges. Yes.
The most challenging is how to find the high purity of zirconia.
Yes. Yeah.
Yes.
That we know. Yes.
Okay. Yes, that's the most challenging because commercially I can find the very high purity zirconia from provided by TOSO. You know, more than 90% zirconium content inside. Yes, we want to increase our zirconia content, maybe up to 80% actually very good. That's not easy to reach that. Then very challenging because after we have the high purity of zirconia, we can do everything. We can produce the solid electrolyte for whether for fuel cell or whether for battery. So the key is the high purity of our raw material to find the better material for the process.
Okay, this is a next question. Okay, how to implement your sample for the real-time applications? Because we are the science people, we cannot make any real-time applications. We are challenging, right? The science people getting challenged for making the device.
Real-time application?
Yes.
You mean near time? Or?
Yeah, that means model making any prototype model. For example, when you doing research, okay, our findings to the practical applications. this is challenging for us, right? Quite
Yes.
challenging for science people because we don't have that much knowledge for making the development. Okay, you can tell us.
Yes.
Uh,
Of course, I has fabricated also a prototype. As also
okay.
a prototype. But as I show you that this is still ongoing this year, and I cannot share out because of the company that funded my research project. And the result is, yes, the battery can be charged and also can be discharged, but the efficiency is still very low. It's about only 7%.
Yeah, 7%.
Yes, yeah, I can charge the battery, but when discharging, the current that come out still very low. And
That I agreed. Actually, we done it for efficiency and everything. But commercialization is possible for science people. Commercialization.
Commercialization.
Yeah.
Yes, of course. Some research estimate that probably on the next 10 years or 15 years, the all solid battery can replace the domination of liquid battery actually. Because maybe on the next 10 years, the electrical vehicle will be produced massively by considering the global warming effect, etc. So maybe, yes, it is reliable, but maybe for the next 10 years or 15 years.
Okay, have you concentrated on any other applications, different applications, only for focus on electrolyte or any other applications? Already I done it, this material for defense application because zirconia have that high temperature, right? So they can use.
There are many applications of zirconia for catalyze by combining metal. Also can be combined with other adsorbent. Okay. It also has absorption capacity also. But because I'm an electrochemist, I just focus on the using of the zirconia for electrolyte or for electrode.
Oh, thank you so much for the brief explanation and your patient, excellent, wonderful presentation. Once again, thank you.
Thank you, Dr. Suresh.
Committee. Okay. Now I request Jipan sir to give the small research aspects of materials today.
Yeah, actually,
share with your experience, maybe film technology or any different applications.
Our main concern and focus is actually on sensing material and all electronic material that we can do actually from the single crystals point of view. That is very important. What about the materials you are searching for better efficiency or better performance or better lifetime, that we need actually the quality of the crystal. So from that point of view, even that may be the optical crystals or maybe the inorganic crystals, organic crystals or semi-organic crystals, that single crystals, that part actually in my lab started with having the experience from the Crystal Growth Center, Anna University, Chennai, and started growing that single crystals using that very simple technique from aqueous solution technique by slow evaporation process or the slow cooling process. So that is the simple technique, and I used actually in my lab, and a few students have done their PhD work growing that organic, inorganic, semi-organic crystals for laser applications. So that part actually is, I think, the people or students can concentrate using that the organic salts, inorganic salts, mixings and preparing the solutions and filtering, and then allow that the evaporation of water from the solutions, and ultimately we can grow reasonable size, very big size, and very perfect and defect free that crystals is possible to grow actually. That is the one side that is academic, as well as I think these crystals have the industrial application also. Second thing is actually we are all concerning the energy concern. That is preparing that the lithium battery or any hydrogen fuel research and whatever that we are doing actually by thin film technology for sensors and thin film technology. That also very important nowadays. All the metal oxides and the semiconductor different groups, we are trying to improve the quality of the film first, because that performance depends on the quality of the film. If we can grow the defects free and perfectly three ordered perfect orientation, and that film or the material will give the better performance. So on that point of interest, we are also growing actually in my lab, in my group. We are using actually very simple technique. We know that we don't have the MOCVD, we don't have that the all other plasma deposition or PLD technique. We don't have actually that, or we don't have that the clean room also. But what we are doing actually, concentrating the selection of the material is also important, and then tailoring the properties of the metals. So we are doing actually all oxides. Basically, the zinc oxides is very promising material, copper oxides, magnesium oxides, titanium oxides, bismuth oxides. So these all series of the binary and ternary metal oxides that we are actually preparing, synthesizing, that the thin film range about 100 to 500 nanometer range, depending on that the duration of the pyrolysis process. So that we got actually the better, what I will say, even using that very simple technique, that we can deposit the very quality film. And we don't use that the ITO or FTO. Even the plain glass substrate is okay for good addition of that the metal oxides. And that is a very good addition and very stoichiometrically, I think that is very good, using that the spray pyrolysis deposition technique. So it is very common, it's very easy, and many people are using that the spray pyrolysis technique, and also the spin coating technique also. That we are growing actually in my lab. Our students are doing, and very good quality films also we have found, and we go for the characterizations. And as you also involved in my group, Dr. Suresh, for a long time, I think actually that collaboration is also important nowadays. Whatever we do from a single lab, we can share our experience, our knowledge, our limitations. So this way actually now we have to think about to extend, to continue our scientific progress, making a joint collaboration. Maybe one unique facilities I have, that other unique facilities maybe you have in your lab. I means you means all actually. So that collaboration is now most essential to keep up and to continue our research. I think this way we can do better research also. And this important thing is actually the using the raw material, low cost material, low cost technique. That is important. Ultimately, our achievement is to reduce the cost of the product. So from that point of interest, we are always looking and searching for the low cost material, low cost technique, and how to improve the actually efficiency of that product. So this way actually in our lab, we are working on metal oxides, binary, ternary, these metal oxides, and students are also very encouraged and very happy when they can communicate to their research in an international journal. And every year that students, they are publishing their work. And I am also happy to be a guide of my students and to guide the students for their, mostly the MSc and PhD research work. So can you please share some experience from Dr. Fitria from your side, or Suresh, or anyone? We can join actually for discussions. We have limitations, we know, but we have the all facilities now. And now people are working from different countries jointly. They are publishing their research work, right? So it is
Yes.
possible because of that the talented people are there. They have the facilities. So the important thing is the coordination and cooperation. So we have to open up our mind. Then only we can progress. Actually, I think this is the way we can carry out our research.
I agree with that, Professor. Collaboration
Yeah.
between countries, yes. Because each of us always have limitation, I think, and if we collaborate each other, we can, yeah, we can help each other to develop our quality in research.
Yeah, this is the first time that Dr. Suresh and Dr. Fatima, they organized this conference actually. So this is the first, and I think stage to make the good bridge among ourselves, right? So among the all participants. So definitely, this is the first step you started, Dr. Suresh and Dr. Fatima, by doing their hard work. And I hope we people are encouraged actually and will be motivated to carry out our research. And next, actually, I have some, I want to know some experience from Dr. Fatima.
Maybe while we wait for Professor to file, I will share about another conference.
Okay.
Yeah, we also have another conference from our department, which will be conducted on 30 September 2020, which is the third international conference on chemistry, chemical process and engineering. So join with us because it is also the online meeting, but then we call for paper from the participants, and then after that we will publish the special issue of the journal. There are two special issues of the journals. The first one is the Open Chemistry Journal, and the second one is the Bulletin of Chemical Reaction and Engineering and Catalysis. Also, the rest paper can also publish in the AIP conference proceeding, which is indexed by Scopus. So for all participants, join with us. You can see the website of the journal in chemistry.uii.ac.id/IC3PE 2020. And the deadline for the last call for paper deadline is 25 July. So 25 in this month. So just submit the full paper, the best full paper you have, so we can publish in the special issue of the journal. Okay, join us, please.
Very good. I have got actually a few feedback from the participants actually. They are asking in joining this virtual conference.
Yes. Mostly positive. Yeah, mostly positive feedback from the participants.
Yeah, they are showing their keen interest actually to deliver their work, maybe for short duration. Maybe next time, if we wish to conduct the conference, maybe we can allocate time for the participants for their presentation for short duration, 10 to 15 maybe few actually participants we can select out of their submitted abstract, so that if we have to continue for a long time due to that COVID-19, then we have to think about the other mode of presentation, because we don't know what is the end of this the crisis actually, right? So maybe after 6 months or
Thank
maybe
you,
after
Jipan sir,
1.
for giving a.
So
Thank you so much, Jipan sir, given the brief introduction about his laboratory and about on the crystal growth research activities. Behalf of NanoCat, we launched a journal, Malaysian Nano, who are interested to publish your paper as a research article, review article. Can you hear me? Hello?
Yes, yes, yes.
Yeah. So our center has launched Malaysian Nano and International Journal, MNIJ. I can send the link to Fatima. She can display in that screen also. So those who are interested to publish your paper, like research article, review article, comments, or any of the small paper letters, so you can publish with us. We will actually shortly we will get that Scopus index in our journal. And another journal, one of my collaborator and the keynote speaker, Professor Wan Chuan Wo, the editor-in-chief of Asian Journal of Material Chemistry. Those who have any papers related with this topic, the Asian Journal of Material Chemistry, you can send it to us. I'm the editor board member, so we can publish your papers in the journal. And third journal also, International Journal of Multifunctional Material and Photoscience. That also they edited by Professor Wan Chuan Wo. So he will support us to publish your papers in that journal. And furthermore, I would like to say that myself and Jipan sir, one of my colleague, Farid, the editor of a Elsevier book entitled Metal Oxide for Optoelectronics and Optics based on medical applications, to be published in the year of 2021. So those who are interested to write the book chapter, that invitation also will be circulated through Fatima. So those who are interested to collaborate with us, you may contact us.
Okay, Dr. Suresh, Prof. Tofel has been joined with us, so.
Okay, we'll start now.
It's your turn.
Yes. Is connected?
Yeah, it's connected.
Yes, yes. Hello, Prof. Tofel. Hello, Prof. Tofel.
Hello, good afternoon and good morning. Sorry.
Okay, Tofel.
Yeah. Okay, please, Dr. Suresh, deliver your session.
Yeah.
Okay, thank you for Fatima. Good afternoon, one and all. I hope everyone enjoyed the previous lecture and acquired more knowledge about topic on zirconia-based material for solid electrolyte. It is time that we start our today final section. Dear participant, now we are going to hear the final section speech, which will be delivered by Professor Tofel, AM Side, Department of Physics, University of Limerick, Ireland. It is now my privilege to introduce Professor Tofel, AM Side, Department of Physics, University of Limerick, Ireland. Professor Tofel AM Side is an associate professor in the Department of Physics, University of Limerick, Ireland, and member of Bernal Institute of the same university. He received an MSc in Engineering and BSc in Metallurgical Engineering from Bangladesh University of Engineering Technology from the University of Limerick, Ireland. He conducted a postdoc fellowship on the surface characterization using X-ray photoelectron spectroscopy and the molecular modeling. He is one of the co-inventors of super resolution chemical imaging using infrared absorption. His research interest focused on converging science towards innovative solution in the therapeutic device, high resolution spectro, microscopic and imaging. With long list of his achievement and glory, I would like to invite Professor Tofel AM Side. Please put light on the topic, virtual nanoparticles.
Thank you, Dr. Sagadevan, and thank you, Professor Fatima. And also I'd like to thank Professor Poddar for making me aware of this conference. This is my first virtual conference, so I will remember this, and my apologies for being late on this. Part of the reason was I had internet difficulty, and also part of the reason is also a lot of those things that I'll be presenting is quite new, and I'm not going to present any data because the data is coming out of an industry-funded project, but I would be able to show you some of the concepts that are publicly available, okay? And we're working towards it. So what the topic that I chose, because I know that this is a catalysis community and nanoparticle community, and a lot of metal oxide would be relevant. So I thought that I kind of highlight some of the missed opportunities that we had in the past, but because of the coronavirus situation, we are now escalating a lot of those things, and there are issues around it. And especially in a time when we all became a little, everybody became an expert on corona, it's very difficult to pass in a new message across. There's a high level of skepticism and also high level of fear. So what I would be requesting that please take all those things that I would be saying, okay, as very, very preliminary and nothing conclusive, okay? Because we are testing now, and I don't have the liberty to tell you all the test results, okay? But there might be solution, but at the same time, please don't take any false hope. Follow the regulation, follow your country's public health officials' advices, maintain social distance and all those things, okay? The solution that we'll be talking about, it will be coming in the market. It will take about a year or two in the most speedy situation. So with that, I start with this very, very grim situation that was published in New England of Journal of Medicine earlier this year, and that gave the foamability of this virus and the spread of this virus from the surfaces. So it means that it's not only the aerosol spread that we are afraid of, it actually stays and persists. This virus stays and persists on a number of surfaces for much longer time than we thought, okay? That makes it extremely, extremely stable, okay? Especially traditionally, we thought that metallic surfaces are antimicrobial, okay? But except for copper, we saw that, I mean, the metal, especially stainless steel, if you look at here, okay, it is actually quite persistent, okay? So now, I mean, I'm from the subcontinent, which is a bronze civilization. So we were very happy to see copper, okay? But this is metallic copper, and there is metallic copper in bronze as well, bronze and brass that is widely used in the subcontinent. And that brings back copper and copper oxide back into the equation, which we have been ignoring for a long time because of our perceived toxicity of copper, okay? So copper nanoparticle and copper oxide nanoparticle would become, one of the most interesting study from this compared to stainless steel, definitely, okay? So that's one thing. However, in the short term, we need to look at the health impact and all those things. So copper has not been well studied in this aspect, in the public health aspect. So there has to be some regulatory approval that we have to take. Okay? I'll just move very fastly because I know that this is the last session and I have only a half an hour, and I deliberately asked for this half an hour rather than making it to drag. Again, this is, and the citations are given, it's also very recent. here they actually looked at the formation potential of different surfaces for coronavirus. So this is SARS CoV-19-2 virus, okay? But another thing that we need to understand, that even though there are differences in specific strains of this virus and it mutates, but broadly it's an enveloped virus having a lipid envelope and glycoprotein spikes. So fundamentally, the structure of this virus is very similar to other coronaviruses. Yes, it is more transmissive, it's more infective, it's more spreadable, okay? But in essence, the basic structure of this virus is very similar to other coronavirus and influenza virus. That does not make it less threatening. Okay, so we need to emphasize that, but it means that if we are thinking of a mitigation strategy, there are strategies there, and I would highlight some of the recent data, some of the recent publication on that. So this is an article that is also published quite some time ago. They were looking at general inactivation of coronaviruses, okay? And they found that, okay, a lot of the microbial agents are quite effective. And of them, I would be highlighting some part here. Look at the hydrogen peroxide. And this is actually tested, okay? And within 1 minute, it gives you 4 orders of magnitude inactivation up to the detection limit, okay? So 4 orders of magnitude means log 4, and it actually does within a couple of minutes. And if you compare with ethanol, which we use for our hand wash, okay, that takes between 30 seconds to 10 minutes for about 5 logarithm reduction. So what is a hand wash doing? We can possibly get the same thing from hydrogen peroxide, okay? And you have other infectious, disinfectant there, okay, which are also effective. And this is where I'd be highlighting that if it was actually used to disinfect the surface of stainless steel, okay, within 2-3 hours of exposure, we got between 4 to 5, about 5 orders of magnitude reduction, okay? And that's hydrogen peroxide that has been used. Whereas in ethanol, it's 1 minute. So the virus is very fragile because ethanol is very simple disinfectant. It's an amphiprotic disinfectant. So that means that it can attack the hydrophobic surfaces and it can attack hydrophilic surfaces. And this is exactly what is happening with coronavirus, because it has a hydrophobic envelope and it is a hydrophilic spikes. So we can get some insight on that may allow, and this is what would be interesting, is on contact killing of the virus. And this is again where some of the metal oxides can play a big role, okay? Because we know that these metal oxides, the photocatalytic metal oxides, when they get ultraviolet exposure, they can crack water and can create hydrogen peroxide. So that's the natural way of creating hydrogen peroxide on surfaces, rather than fumigating them or blasting them with hydrogen peroxide. And the mechanism of hydrogen peroxide and interaction with lipid and other things are already known. So there is nothing to be reinvented here. The question is that what we would be using as an agent, can we use it as safe, within the safe exposure limit, and can we keep it durable? Okay, so here again is published quite some time ago, where they actually looked at the effectivity of titanium dioxide, which is another photocatalyst, okay, against influenza virus, okay, and coronavirus is a sort of influenza virus. Okay, again, I mean, we should not consider it like other influenza virus because of its spreadability and its a huge immune response that it gives. However, there are similarities, and we can develop a strategy. And this is where we see here. I don't know if I can remove this. How to remove this? Yeah, good. So if you look at this, 1 milliwatt per centimeter squared intensity of ultraviolet has actually reduced. If you look at there, within 4 hours, it gave about 5 orders of magnitude reduction in influenza virus. Now, if you ask me that, okay, what does this 1 milliwatt per centimeter squared ultraviolet intensity mean? It means that if you can see the sunny Irish weather here, okay, and I'm sitting just beside, I'm sitting just beside the window, so you can see sunny days. Ireland is well known for its sun. Here is about 1 milliwatt per centimeter squared intensity of ultraviolet coming through the window on a sunny day in April in Ireland, and in July it would be higher. Okay, in July you get about 3 milliwatt per centimeter squared. In Jakarta, I would be saying that it would be much higher, and in Middle East and in the tropics it would be much higher. So you can get those data from the UV I index that the WHO has actually given. Is the UVA that one has to look at, not UVB or UVC, because they are carcinogenous. Okay, so is the UVA intensity what matters, because this is where the photocatalyst absorption band is kind of there. You can get it shifted to the visible, but those can be done. Okay, and a lot of work has been done on titanium dioxide and zinc oxide photocatalyst. Okay, in their chemistry, in tuning their band gap, okay, and getting the absorption band in yellow or green was a huge effort in the past 2 decades. But even the photocatalysts that are out in the market, okay, without changing the chemistry, can be used to coat masks and PPEs, so that the virus under the action of UV, okay, can be inactivated on contact. So that means a couple of things. First of all, when you're going outside in the buses, in the public transport and all those things, if there is sunlight, okay, you will get much more effective lowering of the bioburden. Okay, and that is what I'll be emphasizing. The risk is proportional to exposure. Okay, so if the exposure to the burden of this virus can be lowered, your risk is lowering. So that means that we can then get out. Okay, and of course we have to maintain the caution and all those things, but we do not have the fear factor. Okay, so that is the concept we are trying. The question then would be that would the nanoparticle itself be a hazard? And there is a wide amount of literature where they're saying that nanoparticle can have some adverse health effect. Okay, so the question is the dosage. So there is a balance between how much nanoparticles we will have to use to inactivate the virus, and how much risk that poses to me and other people from exposure. So there is a slight balance there, and that has to be tested. That has to be established, okay, before we start coating everything with nanoparticle. And this is where some of my previous work on the nosocomial infection. Nosocomial infection means hospital-acquired infection. That we were trying to explore would probably be relevant here. Now, one thing that and I'm not going to undermine, I'm not a conspiracy theorist, I'm a scientist, cannot talk without evidence. One thing that we have to understand, that significant deaths by COVID-19 too has occurred in patients who had comorbidity. Comorbidity means that the patient or the person had some underlying medical condition, either very high blood sugar or very high blood pressure or prevalent cardiovascular issues, okay, just to name few. And age was also a factor, because if the patient's own immune system was not strong enough to fight the virus, at some point they needed assistance through oxygen in ventilator, or they had to give up. So that means that a lot of these patients, when they went into hospital, when they were having respiratory difficulties, okay, and it is not well studied, okay, but there is a possibility that they acquired infection in the hospital, and the prevalence is about 10% in Europe and in US. I don't know how much it is in Jakarta, or sorry, in Indonesia or India or in Bangladesh. I don't have the data, but I know that in Europe, nosocomial infection, hospital acquired infection, is a problem because all the superbugs are actually staying there. So there is a possibility that, you know, the situation got worse when these patients went into the hospital. Okay, so there is some overlap there in the interest when we were trying to use this photocatalyst in treating, in fighting the hospital acquired infection. So this is where I'll be going very fast, because this is well studied area and a lot of people are talking about it. So when we go to hospital, we pick up infection. So what we were thinking, that part of these superbugs and this hospital acquired infection comes from the textiles that we have in the textiles and surfaces that we have in the hospital. So we were thinking that, okay, we would be coating these surfaces with self-sterilizing nanoparticles, okay? But at the same time, we will have to keep the nanoparticle to a lower level so that it does not become a problem itself. And this is when what we realized, that, okay, you can actually get quite effective killing of antimicrobes and viruses included there by using photocatalyst, but not to the amount that people were using. People are using too much, okay? So they were actually making an uniform coating on the textile. And if you think that it's a metal oxide, it's a ceramic, and textile is a polymer, so it's a more compliant, and ceramic is more stiff. And if you try to put that in, ceramic does not bond very well. And then what they do is put a binder, and then the binder holds the ceramic and links it with the textile surface. And this is when the binder becomes a problem, because the durability of the coating depends on the durability of the binder. So what we came up with, and we just got a US patent this April on a method where we could put this nanoparticle on the textile without any binder, and it was stable even after 100 wash. Okay, so we have data that we can show, and this is the technique that we developed. Okay, so we used a polyester textile and put titanium dioxide into that. Okay, and we just need to soften the surface and put the nanoparticles there, and it sticks there. We don't need any bind. Okay, so a company has been spun out by my former PhD student, and he is now looking at the antiviral activity of the technology, and we got some promising results as of last week, fingers crossed. But the essence of the technology has been tested against MRSA, E. coli, and other common microbial microbes. Okay, and we can see some of the data here. And the principle is that you don't need a uniform coating. So if you see here, These are the nanoparticles on the PET surface, and you can see for bacteria, this was optimized, designed for bacteria, okay? And you could see that there's quite a bit of gap, okay? Quite a bit of gap. And that gap would be smaller for viruses, because viruses are more kind of an individual nanoparticle. They don't actually form colony, whereas bacteria, they actually form colony. So it was easier against designing against the bacteria, but for virus, we'll have to actually design it in a slightly different way. But this is where I would be trying to finish. So this is some of the SEM images of the textile coated with titanium dioxide. And this is the design principle that I use against bacteria, okay? That is the colony forming that we have to stop. With viruses, it has to be much closer packed, okay? But if we actually design it properly, okay, we should be able to fight this coronavirus, even in a consumer application. You don't need to use medical grade N95 type of thing. It would be a normal mask that WHO is showing, or the CDC chief is showing on the video. You can just have a coating on that and just put it on and walk in the normal day-to-day activities in consumer applications. With that, I would like to conclude this, that okay, we presented some very preliminary concept in using photocatalysts as an effective antiviral coating in consumer use in textiles. And yes, it can be made durable. We have actually made durable it against bacterial effectivity, and it can also be made safe to use even for consumer use. With that, thank you very much for your patience, and apology again for the delay.
Let us thank Tofel and Said for your excellent presentation. Your lecture was very interesting and informative. The participants who attended really enjoyed your presentation. We appreciate you are making a time in your busy schedule and deliver the lecture for us. I hope that participants can learn more about topic on nanoparticle through your presentation. Once again, thank you for wonderful presentation. May I now take privilege of inviting Professor Jipan Badat to say about his student Tofel AM Said.
Thank you, Dr. Suresh. Can you please open the video, start video? Because
yes, I opened.
No, that is the stop.
No, your video is closed. I think.
Yeah, can you start? Okay.
Okay.
Yeah, thank you very much, Dr. Suresh Sagadevan. Actually, you missed something to say about the Professor Dr. Tofel, because I know him very well. So first of all, I want to give a thanks to Dr. Tofel because he is a multi-talented scholar actually, as well as good speaker, good scientist, good writer, good singer also. So I feel proud to introduce Dr. Tofel actually as my ex-student, ex-colleague, as my friend, and he's the great son of Bangladesh. We are very much very proud of him actually. He graduated from our university. He served our university. Now he is working as a professor in the Department of Physics, Burnell Institute. It's the most prestigious institute in Ireland. And he established a beautiful lab actually in his university with his own initiatives. So that is the things actually, few words, maybe more words we can say about Dr. Tofel, and he's a good speaker. I think audience has observed this as he's a voice, his presentation is convincing, everything is enjoyable. We enjoyed a lot actually, Professor Dr. Tofel, and very happy to see you. Your mic is mute, please.
Likewise. Likewise, you are one of my favorite teachers, so that's why I respond.
So actually, we started this virtual conference. This is a very hard time we are passing. So what to do during this time lockdown? So that Dr. Fatima, Dr. Suresh, they initiated better. We can start actually our virtual conference. So we have actually 6 speakers from the different countries, and you people are very busy with your own projects. We know. But to inspire our audience, our young researchers, colleagues, friends, so then we requested, okay, if we can invite, and if the actually the expert peoples, if they agree to join and give their time, so then we'll be benefited. So out of these focus and interest, we started this virtual conference. And definitely, you see that we have an audience about participants more than 160, 70. So normal in physical contact, we may find maybe 40, 50 or 60 participants in the lecture hall. But even you see in the virtual conference is a huge, we cannot accommodate in a single lecture hall that 160, 170 people. So that is the advantage we are taking this virtual conference, and it's cost nothing. So without spending a single dollar, we can arrange. But the important thing is to get the consent of the speakers. And as you agreed, then I think this is the good initiative. We started our actually activities, and we hope in near future also we'll get your actually consent and your cooperation, your help, and in that way we can continue our actually activities, scientific, for the greater interest of the scientific community. Right?
Absolutely, no problem. Yeah.
So this is actually we are almost at the end of the session, but the last 2 days we are very happy and we are inspired actually to see the actually participants, the huge participants in the audience, and full time. That the morning session we had a presentation, 2 presentations, and in the evening session we have also presentations. We have a short break. But today in Bangladesh, that this is the Friday, there is the Juma prayer. But even then, I have seen that all participants are with us during the whole session. So Professor Tofail, we are very happy to see you, because I visited your university last before. But yeah, we enjoyed actually this the facilities, the institute, and what you are contributing to your institute. It's very encouraging and inspiring actually. And I hope all of your colleagues are also fine.
Yes, thank you.
So that Suresh and Dr. Fatima. So what is our next program?
Okay.
Yeah, it is.
Okay, thank you, Dr. Suresh, Prof. Jiban, and also Prof. Tofail. So
it is time that we start our ceremony.
As the convener, we also will send the certificate for Professor Tofail. And again, thank you very much for your contribution. So our conference is about to end. So for this, we will have a closing statement. The first statement, closing speech from Prof. Jiban as the director of the conference, and then closing statement, closing remark from Dr. Suresh Sagadevan. So please, Dr. Suresh or Prof. Jiban first, please.
It is time that we start our closing ceremony. Good evening to one and all gathered here. As we end today's event, I would like to thank you all for joining the International Virtual Conference on Advanced Functional Nanomaterials and their application. Now I call upon Professor Jiban Border, co-chairperson to deliver the validity address.
Thank you, Dr. Suresh and Dr. Fatima. You both are the convener of this conference. And first of all, I would like to mention the name of the institutes. The 3 universities are joining for this conference. Universitas Islam Indonesia, Nanoket, University of Malaysia, and in association with the Bangladesh University of Engineering and Technology. First of all, I would like to thank you all to give us opportunity to be associated with this, to joining this conference and to be a co-organizer of this conference. So on behalf of my institute, as well the other universities, I would like to congratulate, I would like to thank to all the guest speakers of this conference, first of all. So we have the 6 speakers from the 6 different countries. Professor Oun-Chan Oh from Korea. So first day he delivered his beautiful presentations. And Professor Masaya Ichimura from Nagoya University of Technology, Japan. Then Professor Tetsu Soga from Nagoya Institute of Technology, Japan. Professor Tofael Said from Ireland. Dr. Fitria from University of Indonesia.
11 Maret.
Yeah.
Universitas 11 Maret.
University of Maret. And one more speakers, actually I missed his the
Dr.
name.
Witri Wahyu Lestari.
Okay, so
Yeah.
we have 6 actually speakers in our conference, 2 days conference. And this is the virtual conference, and this is our new experience actually, how to conduct the conference. So we are all in different places. But I would appreciate the conveners for their tremendous effort to conduct this conference. And immediately they delivered the certificate of appreciation also in the beautiful certificate they prepared. And this is just to encourage our young scientists, our researchers, our colleagues, our friends. So we are actually thankful to all the guest speakers for giving their valuable time and to share their experience and that is related to the theme of the conference, that is advanced functional nanomaterials and their applications. These topics is very important in the current days and all useful. The applied research, we have seen these 2 days presentations from the expert academicians, the presenters, so that we inspired and we are very much happy to listen their presentations and their talk. So that is the next. Actually, I would like to thank the audience. That is also important because if we have the speakers, if we don't have the listeners or participants, that is not meaningful. So I would like to thank all participants for joining this conference, because this 2 days conference during the lockdown, we are all in different places, different countries, and due to sometimes that the poor connectivity, but even I think this whole conference is not interrupted by any poor connectivity. So we heard actually all the speakers' presentations so nicely. So this is the way we can continue our cooperation. I hope this is the first time we organized this conference in joining the 3 universities, and now we have many friends and many scientists, so we can collaborate our research activities in future also. And definitely when we'll arrange again any conference, we'll circulate and we'll make a good bridge among us. So I think with your participations, with your presence, with your presentations, we all people are benefited in this conference, in this virtual conference. And I hope this conference is enjoyable, and we people all enjoyed, and that is the memorable also, this conference. So this is the thing we earned from this conference in organizing this conference, and this is new experience. And we hope that this COVID-19 will go away and very soon, and our better days will come soon, and
Amen.
definitely we'll meet again physically, and we'll meet our friends again physically in near future. And I wish you all the best, and also good wishes for your good health, and definitely we'll take care of our lives. That is important. Life is very important. That is the only one time we have. So this, to use this beautiful life in the beautiful world, we have to make it. And how we can do it actually by doing some advanced research, and that is for the benefit of the society, to benefit of the scientific community, that we are doing from our side. So we'll keep our cooperation. Definitely will contribute a lot in near future. And again, I would like to thank you all for joining this conference, and for giving your valuable time and your very, very nice presentations. And we enjoyed a lot these last 2 days. And thank
Okay.
you to
Okay,
everyone.
thank you, Prof. Jiban and Dr. Suresh. For another documentation, so we will have the screenshot from the admin. So will be divided into two sections. The first section is for the conveners and also the speakers of today's conference. So just switch on your video for the speakers and also the committees, the conveners, so the admin can shoot the screen for documentation. Okay, wait for 15 seconds. Smile. Okay, the next is for all participants. So please, for all participants, just switch on your video so the admin can shot your photos for documentation. I will give you maybe 2 minutes and smile. Finish, admin?
Ini mah nggak diaktifkan videonya.
Dr. Suresh.
Yes.
Can you give some to say few words? Professor Ichimura is there for profile or any other?
Yeah. I can give conclusion. Yes.
Just wait 1 more minute.
Yeah. Do I unmute? I wanted to see my video now.
Wait.
Okay, the admin has made the screenshot for all of you, and it is the end of our conference. So there are many questions regarding to the certificate. So the certificate for registered participant can be downloaded from this address. So just click this address so all participants can download the certificate. It is already served in the drive.
Yeah, Dr. Fatima.
Okay. Yeah.
Just a few words actually want to get feedback from the audience actually that will be.
Yes. Yes, yes. Okay, so in general, Prof. Jiban, there are mostly positive comments to the conference. So mostly about more than 90% of the participants give the very good feedback for our conference.
No, a few at the speakers.
Beda?
Only the guest speakers, those are available. So just a few words. Okay, Dr.
Okay.
Suresh. Yeah.
Sorry, I can catch your
we have a guest speaker.
Hello. Fatima.
Yeah, yeah.
Hello, Professor Fatima. Can
Yeah,
you hear me?
yeah.
Actually, the
Yeah,
difference.
yeah.
You may call any three participants for the feedback regarding our conference.
Oh, okay.
Okay, you can invite them.
Yes,
Yeah.
actually.
Yeah.
Okay. So, okay, maybe one or two.
Yeah, enough. One or two is enough. Yes.
Yeah, yeah. But actually, from the link we have sent for collecting the comments from the participant, mostly positive feedback. But maybe one or two participants will give comment in the screen, please.
In the screen, they can give the feedback.
Yeah.
And also from the, yeah.
Oh. Okay, Pak Ganjar, maybe you can deliver the result. Pak Ganjar, can you describe the result?
Yeah.
Okay, hello, Professor Fatima.
Just give brief result for the.
Okay. Thank you, Professor Fatima. This is maybe everyone can see the result from the share screen, and overall the participant has give the positive comment. Like maybe you can see on the screen, and overall, I think that the conference have good organized. This is the comment from all the comments from the participants. Okay, thank you for this, Fatima.
Okay, thank you very much. So this is the end of our conference. So thank you again for all participants and all speakers for today's conference. And see you again. Maybe we can conduct another conference next time. We will inform you. Okay, thank you very much. And Assalamualaikum warahmatullahi wabarakatuh. Goodbye.
I will give us a conclusion. Fatima.
Okay, just please.
Yeah, I feel.
Yeah, okay, please.
Can I stop? Yeah, I feel honored and privileged to deliver the conclusion of this 2-day program, International Virtual Conference on Advanced Functional Nanomaterials and their application. We have been listening to eminent speakers deliberating in the different areas of since today and yesterday. All these valuable insights gave us a new perspective that one should adopt while discussing these issues. This concludes a remarkable, memorable, and knowledgeable event, International Virtual Conference on Advanced Functional Nanomaterials and their application. This may be the end of the today's section, but undoubtedly this is a new beginning. I show my heartfelt gratitude to the professors and all the participants for their wholehearted support rendered in the success of this event. I hope we would learn new ideas from each other, which we could adopt to further improve our work in this important area. I know that there have been many interesting and useful presentations yesterday and today. I believe many good experiences have been shared and good lessons learned. Many people have questioned and interact with the speakers. Thank you everyone for your time and patience. We are extremely privileged to have all here today. Furthermore, we appreciate your valuable time and patience you have shown today. Additionally, I would like to thank our guest staff for giving their valuable time and sparkle of our event. Furthermore, I would like to thank Professor S. Fatima and her team for their hard work in arranging this event. Ladies and gentlemen, you have participated actively, and I am sure you have enjoyed, shared, and acquired more knowledge through this conference. So I am thank you once again for your participation and wish you all the very best. Thank you. I hope based on your cooperation and strong support, we may conduct another international virtual conference in the future. Thank you so much for your patience and participation. Thank you. Wish you all the very best.
Okay, thank you very much, Suresh, and all participants. So this is the end of our conference. So Assalamualaikum warahmatullahi wabarakatuh and goodbye. See you.
Okay,
thank you
all.
very much.
Thank you, Prof. Jiban, Suresh.
Universitas Islam Indonesia, padamu kami berjanji, majukan studi, niatkan bakti untuk pembangunan Pertiwi. Syariat Islam amalan kita, berdasarkan iman dan tauhid, dengan cakra menyatakan semoga Allah meridhai bumi. Universitas Islam Indonesia.
Februari itu 4 kali, 12 kali.
Kami berjanji, majukan studi, giatkan bakti untuk pembangunan Pertiwi. Syariat Islam amalan kita, tegakkan iman dan tauhid, dengan cakra menyatakan semoga